Welcome, everyone. Can you hear me? Is the system working? Perfect. Okay, so today we will keep discussing random walks and weakly hyperbolic groups. So last time we gave all the somewhat preliminaries and discussed a little bit about some examples of hyperbolic groups and things like that. And today we will discuss a bit more of the techniques of proof. So recall, so what is the setting? So the setting is that you start with xt, in this case, is a geodesic separable. Again, the assumption of separability, in fact, can be removed, but we'll keep it for simplicity. So delta hyperbolic metric space. So this is like, as we mentioned, it's a space where every triangle is thin in the sense that, yeah, there exists a delta such that every triangle is delta thin. Basically, another way of saying this is that, yeah, for every triangle, the radius of the end circle is basically delta, or at most delta. Yeah, maybe you have to change delta by 2 delta, depending on which definition you're using, but that's basically it. Okay, and then we say we have a G group, countable group of isometries. Countable. And we say, and the measure mu on G is non-elementary if the subbing group generated by the support of mu, the subbing group, contains 2 independent loxodromic elements. To recall, what is a loxodromic element? Well, loxodromic element is an element for which the translation length is positive. So in fact, such element has 2 fixed points on the boundary, and in fact, the dynamics looks like that. So there is an element G that sort of translates on a quasi-geodesic from one boundary point to another, and another element H that does this. And independence means that these fixed points are disjoint. So you have at least this 4 fixed points. So again, loxodromic, G is loxodromic if the translation length, the tau of G, which is the limit, then goes to infinity of O, G and O divided by N is positive. So in fact, so the theorem that I proved with Joseph is following, that I mentioned last time, is that in this situation, so let mu be an elementary measure on G, group of isometries. And okay, you take O in X, then, well, the first thing is that you have boundary convergence, and the limit, almost surely, the limit and then goes to infinity of W and O exists on the boundary of X. In fact, we will remark a few more. We give a definition of the boundary because we still haven't given it. But the second is, as I said, that there exists some L positive such that the limit of the drift is at least L. And again, if the finite first moment exists, then the limit exists. In fact, another thing that I didn't say is, if you care about loxodromic elements, is that at least, then this can be improved, but at least there exists L positive such that the probability that the translation length of Wn is bigger than L times n goes to 1, and n goes to infinity. So as a corollary of this, you will have that the probability that tau Wn is loxodromic also goes to 1. That's because loxodromic means that this is positive. And in fact, that this doesn't just show that this is positive, but rather it shows that the translation length is linearly growing with the number of sets. So L is some number. In fact, it turns out that you can pick L to be any number which is slightly smaller than the drift, if the drift exists. So yeah, and in fact, you can say more complicated things about. So this is not the very first term is 1, and this is what we did. But then more recently, people have done more sophisticated other terms in this expansion. But yeah, so for instance, so this gives the somewhat very famous corollary that was due to Meyer before our work, which is indeed for if you look at the action of the mapping class group, the probability that Wn is Pseudo-Nasov goes to 1. So this is, if you think of G to be the mapping class group and X is the curve complex, then loxodromic elements there are Pseudo-Nasov elements. So that's an easy consequence. And so this, in a way, this is a generalization to any action. However, famously, this problem is still open if we replace the random walk model with a counting model. So instead of doing the random walk on the group, we take the graph and the KD graph, and we're looking at a ball of certain radius. And so you want to know how many elements in this ball are Pseudo-Nasov. And so this is also conjectured to go to 1, but this is a much harder problem because you don't have this Markov chain model, but you have balls, and it's much harder to describe the sequence of balls. It's not a Markov chain, so it's harder to. Okay, so this is the statement. Maybe any questions about the statement? Or?
So this was always about the balls.
No. This is about the random walk. Yeah. Okay, so this is today we're going to talk about 1. So we already looked at the convergence problem for random walks on the hyperbolic disk. So this is Furstenberg's proof, and so our proof is a bit of a generalization of that. And there, there was an important ingredient in the proof for x equals the disk, which you already saw. And this, we were looking at the space of probability measures on the boundary of the disk, which was a circle, of course. And then we were constructing a stationary measure. So the most important point was that the first point is that existence of at least one stationary measure on the boundary. And again, the way this was proved for the disk for x equals disk, well, you know that the boundary is compact. This S1 is compact. And so the probability, the space of probability measures on the boundary is compact. For the Wickstar topology, and then you create a stationary measure by just taking any measure and you push it forward by the dynamics. You do this averaging with this Markov operator, and any limit, yeah, you take a Cesaro average, and a limit point is stationary. So right. So the idea is to take any, more or less, any lambda in the probability space on the boundary and consider, well, as I said, we consider sum of mu star k L lambda kappa equals 1 to n, 1 over n. And then you can take any limit point. This is a classical statement, but here we're using the compactness very heavily because we're taking just any limit point. So the general problem is that, and we will see in a second exactly where some examples are, if X is a non-proper space, then the Gromov boundary, which I'll define in a second, is not compact. So this step for proper hyperbolic spaces, you can do the same procedure as for the disk. But more in general, for non-proper hyperbolic spaces, then this is not going to work. And so the main idea that we had is to use two different compactifications for this. So the idea is compare two boardifications. So one is compact and the other is not. And so again, so one is the Gromov boundary. And the other is the Hor function boundary. That I'll call XH. Yeah, okay, if we want to say boundary, maybe just the boundary part of it. Otherwise, the whole compactification. So we'll see that those have advantages and disadvantages. So this is not compact, but it captures the geometric picture that we want to say when we say convergence here. It captures the correct topology. This is compact, we'll see, but the topology is very weak and somehow weird. So we have to, think about what it means that that there's convergence in this space. So we'll see how it goes. So this is the kind of nice idea. So okay, let's see. So let's start with the Gromov boundary. So there is a more intuitive definition of Gromov boundary, which is if X is proper, then we can just define the Gromov boundary like that. So you start with the usual base point, and you consider the following. You consider the boundary of X to be the space of gamma from X, geodesic rays from 0 infinity to X, geodesic ray, starting from 0. And then you have to quotient under certain relation. So what is the relation? The relation is that gamma 1 is on the same class as gamma 2 if the supremum of the distance between gamma 1 t and gamma 2 t is bounded. So what does it mean, right? So in our space, you start with a base point, and you consider all the geodesic rays. So geodesic embeddings of the half line into X. And it's okay, so this is gamma 1. But now, if you have another ray, gamma 2, that fellow travels gamma 1 at bounded distance forever. So if this distance is bounded forever, then we say that these two rays converge to the same boundary. That's the only. In fact, you can note, however, that if you are in the simple case, so if X is a disk with the Poincare metric, well, indeed, the boundary is exactly what you would think. So the boundary of X is indeed S1, because for each point in the boundary, you can produce a ray. And moreover, if you have two rays that converge to two different points in the boundary, well, they diverge. In fact, they diverge exponentially. So if you take two geodesic rays in hyperbolic plane, well, I mean, if they're not in the same direction at a point, then they start diverging exponentially. So I mean, okay, what is exponential is the area, like, yeah, the distance is just linear. Yeah. Right, so it's just, if you take, this is gamma 1 of t, gamma 2 of t, yeah, this distance is 2t basically. And the reason is pretty obvious from the definition of delta hyperbolic, is that if you take a geodesic from these two guys, yeah, it will follow travel close with that. So this distance is almost 2t. So it's really in any way it's definitely not bounded. So okay, so that's the definition. But however, when it's not proper, then it's a bit more complicated, because it's not always true. Yeah, so if you do this, there will be too few boundary points. So, well, in fact, there's two ways. One is you could replace geodesic with quasi-geodesic. So if X is non-proper, you can replace the word geodesic in the definition with the word quasi-geodesic. So you want a quasi-geodesic embedding of half line. But also another way of talking about this is looking at sequences, which is useful for what we do next. So maybe we should do it anyways. So we have to talk about Gromov sequences. And to do that, we have to talk about Gromov product. So again, given 3 points, given 3 points x, y, and a base point O in your space, we define the Gromov product of xy based on O as 1/2 distance between O and x plus distance between O and y minus distance between x and y. So what is this? So let's suppose we are in a tripod. So this is 0, x, and y. Suppose that this is really 0 hyperbolic space. So we are really in a tripod like that. Then if you think about what are we writing here? Well, we are counting the distance from 0 to x. So this we're counting with plus sign and plus sign. Then we're counting distance from 0 to y. So this is counted twice with plus sign. This is counted with plus sign. And then we're counting, we're subtracting the distance from x to y. So we're discounting minus and minus. So in the end, if we are in such a situation, what would the Gromov product be of such point? The Gromov product of x and y with respect to O is nothing else than the distance between O and the geodesic between x and y. So that's why we use this definition. The idea is we want to say from the point of view of O, whether x and y are far from each other or close to each other. And the idea is that, you see your point of view of O, if x and y are close to each other from the viewpoint of O, means that if you draw the geodesic from x to y, well, this is far. Is far from. So in general, you note that if x is delta hyperbolic, you do the Gromov product from x and y at O. It turns out this is always the distance between O and the geodesic from x to y plus an error term. And this error term only depends on delta. So this sign O of delta will always mean some constant that depends on delta, sort of universally. Usually it's like 4 delta, 11 delta, something like this. But of course, you don't want to keep track of what is the exact multiple. So it's just something that depends on delta. So it's fixed on the space. Okay, so why do we care about the Gromov product? Because we can say that a sequence, so to define the boundary with sequence, we can say that a sequence xn of point in x, it's the Gromov sequence. Yeah, if intuitively diverges. So how do we say that it diverges? We say that the limit as m and n go to infinity of the Gromov product between xn and xn with respect to O is infinite. So this is so it means basically that the sequence of elements are sort of going towards infinity, and somehow, yeah, they're getting further and further from 0. So yeah, you also notice that this is over sup or if over m and n goes to infinity. So it looks a lot like the definition of Cauchy sequence. Think about it. So in fact, that's kind of what we want to think of once we eventually will define a metric there. And then, okay, we introduce an equivalence relation. So two sequences xn and yn, well, are the same if the limit, again, of xn yn goes to infinity. So again, the idea is something like this, that you have xn, you have yn, and here you have xn plus 1 and yn plus 1. And you see this distance sort of keeps going like that. And also, since both of them are Gromov sequences, means that also this geodesic is far, and this one is also. Okay. And so the definition that you could give is that the boundary of X in general is the space of xn Gromov sequences divided by this. So this space looks much bigger, much more, scary, because you're looking at the space of all sequences. So maybe it's really like a lot. But it turns out that indeed, yeah, it does not really contain extremely many more points, but of course, but it is more flexible when you don't have really geodesics to play with. In fact, even if the space is not geodesic, you could still give this definition. So, right. So, yeah, the thing is, okay. So the theorem would be is that boundary of X is a metrizable space. So it has a metric topology. And the proof, okay, we give some, kind of some hint. What is the construction? So you start with a epsilon some parameter that eventually, it just has to be not too big as compared to delta, but could be. Doesn't matter. You can produce a metric for each epsilon sufficiently small, and you define the following. So you define rho of, okay, so first of all, given two boundary points, so psi is the class of xn, and eta is the class of yn, two boundary points in this definition. We define the Gromov product between psi and eta to be, again, basically, the limit as m and n goes to infinity of the Gromov products of xn and yn. So basically, you try to take a limit of the Gromov product in the finite case as you go to the boundary. However, unfortunately, the limit does not always exist. However, what is good is that the limit and the lim sup are within bounded distance of each other. So that's where things work. So the hyperbolists, so this so far would be true in every space, but then so delta hyperbolic implies that if you do this construction, the limit of these guys and the lim sup these are bounded by some constant that is O of delta. So you cannot quite take the limit, but you're not too far off if you do take the limit. I mean, you take the limit somehow. And that's how you define this metric. And I mean, the fact that you're off by this O of delta is kind of annoying, but that you always have to carry this O of delta. That's the point of Gromov hyperbolic spaces. Basically, you pretend everything is a tree or something like that, but you have to carry just this additional information that this constant is everywhere. So okay, and then you define rho of psi eta to be e to the minus epsilon this global product. And this is not quite a metric. This is the kind of annoying thing. It's not exactly a metric. So because it's all delta creates it's slightly annoying. So not yet a metric. So it does not satisfy the triangle inequality. But so you define it so that it does. So you define dxy to be the infimum of the sum of rho. Yeah, rho xi yi, xi plus 1 maybe. Yeah, all changed. So such that, yeah, x0 is x and xk is y. Yeah, so the x's are just chains. So you don't know exactly. So So if you want to go from x to y, well, it may be shorter to go from x to z and z to y. And so you define it like this so that you do you do satisfy the triangle inequality. So in fact, note the following, that now D is a metric. D is a metric on the boundary of X. And in fact, it's not too far off from rho. So in fact, there exists C again, which depends on delta, such that, well, clearly it's smaller than rho. You know that. But it's not too much smaller. So maybe let's say exists C less than 1, such that is at most 1 minus C. Okay. So okay, this becomes symmetric. Now, the issue here again is that the issue here is that this may not be compact. So to note that the boundary of X need not be compact. And the easiest case, it's a very important case that for us will be this following case, X, that I call the infinite hydra. Which is the following. We take infinitely many copies of a half line, and we just join them at a point. So we construct the following, right? So we take Z, we take R plus times Z, or times N, and we quotient like this. We quotient the zeros are all the same. So 0, N is the same as 0, N. So you take this countably many half lines, we just join them at a common 0. So this space is absolutely delta hyperbolic. It's a tree. So delta is 0. But the problem is, of course, the boundary here. Well, the boundary is discrete. So the for each such ray, there is a boundary point, and the topology is discrete here. You cannot converge, if you're close to this, if you converge you to here, you're far from converge you to there. Because in order to go from there to there, you have to go all the way back. So there's no other option. Okay, so this so this shows that the boundary need not be compact. Okay, so this is the basic the description of the Gromov boundary for non-proper. Of course, it was also from proper spaces. And are there any questions?
It's incredible.
Yeah.
Only the space is parabolic.
Sorry?
I mean, volume is zero, so your axis is assumed to be parabolic.
Yeah, axis is assumed to be hyperbolic. Yes. Yeah, because we want this. Basically, the hyperbolicity is comes in this in here. Because the construction could exist. Yeah, I mean you could do the construction, but then you might get a really bad space like non-Hausdorff or stuff like this. Yeah, exactly. Yeah. If other questions?
And if the axis is proper, then necessary to be compact.
That's right. So if X is proper, then the boundary is compact. So that's the classical. In a way, that would be the original construction of Gromov. I don't think non-properness was really very much in his mind at that time. Okay. So now the other one is the Hora function compactification, which also has a long history. But in its full generality, well, you have to be careful how to deal with this. So the Hora function compactification, as the name suggests, is compact. Okay, again, we have a base point. And now we can consider the following. For each point Z in a space, we can define the following function, rho Z of X. And it's basically the distance, so it's the difference between two distances. So it's basically the distance from X to Z minus the distance from O Z. So this function has two interesting properties. So the first property of this function is that rho Z of 0 is 0 just by construction. And the second is that rho Z is one Lipschitz. Right, that rho Z of X minus rho Z of Y is at most distance from X to Y. It's just by triangle interval. And so the idea of the Hora function compactification, even already in the classical case, would be to take limits of such functions. Sometimes such functions are called Boseman functions. So, or Hora functions. So, okay, so the definition is the following. So so now we can consider the space of Lipschitz functions, one Lipschitz functions vanishing at 0. So these are f from X to R, such that f of 0 is 0, and f is one Lipschitz. There's a space of functions. And now you can see that there is an embedding here. There is a function from X into this space. You see Z maps to rho Z is a well-defined map. It turns out to be injective. So and the trick, so now we have to consider, they have to put a topology. So X already has a topology. So what is the correct topology here? Well, of course, there's various choices. But for our purposes, especially if X is non-proper, we take the topology of pointwise convergence. So we endow lip 1, 0 of X with the topology of pointwise convergence. So this is a fairly weak notion of convergence, of course. Because of course you could say, okay, you could say uniform convergence. That would be much stronger, or uniform on compact sets, much. But this is since X is non-proper, there's a difference between uniform on compact sets and uniform on bounded sets. Yeah, actually, pointwise is equivalent to uniform on compact sets, because compact sets are basically limits of points. But uniform on bounded sets is much stronger, and it's not good enough. It's not good for our purpose. So, and so what's the definition? So we define the Hor function compactification as is the closure is, yeah. So let's call this map big rho is as rho of X closure in lip 1. There's the closure with respect to this weak topology of this. So this is actually very nice in some sense. So, okay, so here's a lemma, which is very important, is that if X is separable, I don't think we need hyperbolic at this level, then the Hor function compactification is compact and metrizable. In fact, we are never going to use the metric on this space, but we use the compactness. But at least the fact that it's compact metrizable means that it's a nice space from the point of view of measure theory. It's just as good as the interval 0, 1. It's like it's a polished space, everything is nice. Okay, so yeah, so the proof of this is basically to say, right? So the space of functions. So you see that since this is the pointwise convergence and H is Lipschitz, since right. So okay, so you take H in H bar is 1 Lipschitz. So you take any point for any X in X. Well, H of X. How big can H of X be? Well, H of X is H of X minus H of 0. But H of 0 is 0 by definition. So this is less than the distance between O and X. So this function have a uniform growth rate, linear, at most linear base. And so the point is that now we can find that we can map rho of X bar into this infinite product of spaces minus distance of X, distance to X, where X is in X. and this space, you see this space is compact by Tikhonov's theorem. It's a product of compact space. Even though a lot of them, but the weakness of the topology, if you think about it, tells you that the product topology on this is the correct topology. It induces the pointers topology on here. So it actually is fine. So as usual, you have a weak topology, things are more likely to be compact. I mean, this is not so strange, but and in fact, if X is separable, yeah, so the metrizability, and so and our X is closed, so yeah, so it's compact. So why it's compact? Well, the metrizability you get from the separableness. So I mean, this is a classical metrizability theorem. If we state correctly. Yeah, so the space. Yeah, so it's a second countable. So if X is separable, then the space of comp C of X, the space of continuous functions is second countable. And so this one is also second countable. And so this is and it's Hausdorff. So this is Hausdorff and second countable. So it's metrized. So that's so yeah. So lip 1 of X is Hausdorff plus second countable. So it's metrizable. So the only thing we care basically, what this means is, okay, we have this countably many points where we can probe the space. And so the space is not too big. And so the space of functions on this countably many points is not too big. And so that's the reason here. So anyways, we don't care, again, what is the metric? Yeah, the metric, yeah, this is non-constructive. But we only care that this space is an honest, so to speak, compact space. We can think of it really in a bit easy, like in like a concrete compact metric space, as it's in. So example, so again, when you have this infinite hydra. So okay, maybe let's say an easy example, good example first, and then like tricky example. So the good example again, if you take the disk, so what is a Hora function here? Well, you've probably heard of Hora functions before in the classical geometric context. And in the classical geometric context, usually you define, usually you just define the Hora functions in a similar way along geodesics, right? So in the classic metric context, yeah, if you take a geodesic, if gamma is a geodesic ray, well, you define h of gamma at x as the limit as t goes to infinity of the distance between gamma t and x minus t. This is the sort of classic definition of Boozerman functions or Hora functions in the geometric context. It's the same definition because, right, so gamma is, psi is a boundary point, gamma is here, you take your base at 0, so gamma of 0 is O. So the distance, so you pick a point gamma t. So you're taking the distance, so t is the distance, yeah, right. This is the same as the distance from gamma t and x minus distance from gamma t and O. So this is the function rho gamma t of x. So you pick another point, and you take in the distance between gamma t and x, and the difference between this. And then you can check that in the limit, you get that gamma t converges to a point, you get this good old Horo function and Horo cycle. So the level sets of this function are circles that are tangent to the Crookes psi. The level sets of H gamma are circles tangent to the boundary of G. So for every geodesic, you can do this. And all these functions are different, clearly, because the level sets are different. And what is not obvious, but it's true in this case, is there are no other things. If I take a limit of such objects in this functional space, I have to converge to one boundary point, and the function has to converge to such Horo function. So there is a bijection between the geometric boundary and the Horo function boundary. But in the non-proper case, or even in proper but metrically more complicated cases, then things get trickier. So let me conclude by pointing out two examples. So the second example is X is a ladder, so to speak. So for instance, this could be the Cayley graph of Z times Z mod 2Z, which with the obvious generating set will be obvious in a second. So you take two copies of Z, and you connect them by a bridge, like that. So it's clearly ladder. And now you can see that the Gromov boundary and the Horo function boundary are different. So in this case, there are 4 Horo functions up to, yeah. So because you can go, you see, you can start from here and go like that. So this is H1. Or you can start from here and go like that. This would be H2. Or you can start from here and go like that, and this would be H3. Or you can start from here and go like that, and this is H4. So you have 4 rays, and each of those rays gives rise to different Horo function. So, yeah. So the Horo function boundary, so let's call it like that, which would be bar minus H, has 4 points. Yeah, you can say, because you can think about, you see, you could take any sequence of points going to infinity, but every sequence is either has infinitely many points on the upper part or infinitely many points on the lower part. And in order to converge, you have to pick one of the two eventually. So it has 4 points, but the Gromov boundary, in the Gromov boundary, so without H, well, you see that H1 is equivalent to H2, and H3 is equivalent to H4. So the Gromov boundary of X has 2 points, because these 2 rays are fellow traveling each other. These 2 rays, the one that goes like that and the one that goes like that, clearly are fellow traveling each other. So you see, even another way of thinking about is that this space is quasi-isometric to a line, and the Gromov boundary is quasi-geometrically invariant. So it better be that the Gromov boundary of this is the same as the Gromov boundary of the line. But the Horo function boundary is not quasi-isometrically invariant, and it has more kind of, you can think of it as having more points. But then, okay, even more interesting is then X is this infinite hydra. So that is a fascinating boundary, because we know that the Gromov boundary of that is in bijection with Z, so it's discrete, non-compact. Because you can go, as I said, you can go to infinity along any of these lines. This gives you different boundary points. But what is really cool is that the Gromov, the Horo function compactification is more tricky. So because see what could happen. So what happens is, suppose I take a sequence where at each step I'm going to the right and I'm also going sort of upwards. Right? So let's consider the sequence Zn, which is Nn. So I'm going to the right, but I'm also going towards infinity. Now what happens? So this compact space, so there better be a limit. But the answer is, what is the limit? So if you take the limit of rho Zn as n goes to infinity, well, how do you tell the limit? This is the pointwise convergence. So you pick a point, okay, pick a point on this branch, X. So how does the Horo function look like? Well, if I pick this Horo function based at this point, the Horo function starts at 0, goes down, and then goes up. And it's like that. But then if you pick this point and I look at the Horo function based at here, this is the minimum, goes to 0, and then goes up again. And that doesn't change, because basically you're looking at this ray. When the Horo function, the center of the Horo function is under that ray, that you have this perturbation. But when afterwards, when the Horo function, the center of the Horo function is on another branch, the Horo function becomes constantly just increasing. It's just linearly increasing from 0 to X. It's not going to change anymore. So what is the limit? The limit is the function that is 0 here as in increasing linearly on every branch, because this is a pointer limit. And so what is the limit? This is just rho. What is the limit? What is a function that is 0 just at 0 and just grows linearly on all branches? Yeah, but in terms of these Horo functions, it is one of them still, actually. This is just rho 0. Just the distance from 0. Right? So this is just rho 0. So the very strange phenomenon happening here is that you have a sequence of points, Z1, Z2, Z3, Z4, that geometrically is sort of going higher and higher, so kind of to infinity. And it's going sort of going through all the branches. So it does not converge in the geometric Gromov topology. But it has to converge somewhere, because this is compact. And it converges to the origin, which is insane. So you see that this pointwise convergence topology is highly non-intuitive. There are certain non-intuitive phenomena. So that's the price that you pay to get a compact space. But the compact space is yeah, we will see that this is essential to have the compact space. And then you want to go back and relate this to the original boundary, because you still want to prove things in the geometric sense, not in this way. Okay, very good. So we're done. for today.